Okay, so how's your quiz? Have you checked the email? You get the email? Please check your email in the university email. Okay. So how's your quiz? Are you happy with the score? Okay, I think some of you get above 70. Some is in the middle range, 50, 60. Some in the maybe 40 something. Okay, I think from 40 to 60 is average. I mean, at least that is for me as a starting point. That's still good. Okay, that's still good. But if you're having around 30 or below 30, meaning you have some problem with your concept, okay? Your basic concept of math. Okay? So if you have like 30 something or below 30 or even below 10, it means you doesn't have the required concept for the calculus. So you need to have, how to say that, you need to take a lot of efforts, okay? A lot of efforts to study math in basic, okay? So yeah, I think 40 something, around 40, 50, 60, that's a good starting point, meaning you have required knowledge for the math concept, okay? But not really that deep for calculus, okay? So you can keep study and achieving better in the next results, okay? So I will have, so how my scoring will be is it depends on how average the class, okay? So if average class is having some score in 50, 60 something, it will be my standard for making C or D, okay? So based on the distribution of all of the classes. Okay, please check the quiz and if you see any abnormality, something weird that maybe you need you can have better score, please come to me. So for today's course, I plan to have going for implicit differentiations, okay, and maybe some Lopital rules because some of you are already using Lopital rule to solve the problem, but some doing it in a wrong way. Okay. 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 If you have functions, okay. 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 Imagine you have these functions. Uh, square root x plus square root x plus, and it will be plus 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 infinitely amount. Okay. So can you find the first derivative of this function? Okay. So in one clever way, okay, we can solve these equations easily, okay, by implicit differentiation. So I will go for the basic for implicit differentiation, and we can try to solve this one. Okay. Okay. So I will write the implicit differentiation first. Okay. Let me write this graph. Okay. A circle. Okay. What is the equation for circle? Remember? Okay. X squared plus y squared, right? X squared plus y squared. Let's say we have 5. The radius is 5. So if you have 5, it means it's 5 squared, right? Okay. Now these functions, okay, these circle equations, it has x and y. Okay, it has x and y. It's not fx, right? Not equal to fx. Okay, this is the f, x, and also y. It's 2 variables. Okay, so the question is, can we do something related to differentials? Can we derive this? Okay. So imagine one point, maybe here, it's p, or maybe around here. This is also the radius 5, right? So see the triangle here. So the easy one for 5 is having 3 and 4. So it's having 3, 4 as point P. Okay. So imagine this point P is going here, moving. The P is moving. Okay. So when I draw the tangent in P, it's like that, right? The tangent. When the P is moving, the tangent is also moving, right? It's like maybe like this. And when it's moving to here, it's like this. Okay. The triangle also changed, right? The triangle, that red one, when you're moving here, it becomes this triangle. And when you are moving here, it becomes this triangle. Okay. What does it mean? It means your dy and your dx is changing, okay, based on that movement. Okay. So when P is going here, dx will be larger and dy will be smaller. And similarly, when it's going backwards, the dx will be lower and dy will be larger. So as speed moves, dy and dx is changed. But when dy is larger, dx is smaller. And as reverse, also dx is smaller and dy is larger when we move backwards. So the gradient is also changing. Okay. So what will happen? Okay, if the x squared plus y squared equal 5 squared, we try to derive this with x. Okay. I think some of you already learned how to solve it in implicit, but let me show you the practical way first, and then showing you why it's like that. Okay. So what we are doing here is actually, let me write step by step. Okay. So let me write d dx of x squared plus, okay, d dx of y squared. Okay. And let's just have the constant as 0. Okay. So see here, if you're just having x squared and you want to derive that relatively to x, with respect to x, it's easy, right? Because it's your variable and you differentiate with that variable. Okay. So x squared just becomes 2x. Okay. And what happened with y is I will teach you in a practice way first. Okay. So let y be some x. Okay. So if y is x, it's just 2x, right? So let's just write 2y. Okay. Just write 2y. But because it's in x, okay, you need to multiply with dy dx. Okay. This is a practical way to implicit differentiations, how to differentiate any equation with y inside that equation implicitly. Okay. So implicitly, we treat the y like x, and we add the multiplication of dy dx. So this is actually from the chain rule. Okay. So because it's y is canceling, that's why we can write the dy into 2y and still dy dx still there because it's something left behind by the chain rule. Okay. So this is the full equation for the y squared. Okay. So you derive the y squared as like x. It's y, right? So it still have 2y. So I can rewrite the ddx of y squared and write the ddx as the product from the chain rule. Okay. So the chain rule is from this d dy, okay, and dy dx. Okay. So every time you have the y squared or y something y, okay. So when you have any x plus 3y maybe plus y squared, okay, maybe equal 0. If you try to differentiate this, it becomes 1 and then 3 multiplied by dy dx and plus 2y dy dx. And which one is the first derivative? You need to solve dy dx. So dy dx, so from this one, the x squared plus y squared equal 5 squared. Let me write this to the left side. So we can write this 2x or 2y and then we solve dy dx. So this is the first derivative. The first derivative of x squared plus y squared 5 squared. And the same thing happened here. We need to solve this this derivative. So yeah. So after you derive all with the ddx as your tools, derive all, and then solve for dy dx. And that is your first derivative. Okay. Okay, so basically the implicit differentiations, okay, uh, it is really useful even for proving some formula that we have already know. Okay, we can proving the, for example, let me write here. Okay, we know that if you have the power rule, okay, we know that we have this n x n minus 1, right? So let me use implicit differentiation also to prove this statement. Okay, we can write y. So let y be x to the n. Okay, I will have this, and then let's add log, okay, ln. Okay, let's add ln here. Okay, I can do that. Okay, and then ln y is n ln x. Okay, okay, let's differentiate all using implicit differentiations. Okay. Ln y becomes 1 over y. And don't forget dy dx. Okay. And n is just a constant. Okay. It's just a number, any number. Ln x become n over x. Okay. So dy dx become y. Let's back to original equation. Y is x with the power of n. Okay. So I'll write x n over x n. And I will rewrite this form becomes n x n minus 1. Okay. So we can also use the implicit way to prove our basic formula in derivatives. Okay? And it is really useful. You can use that in most of equations. So if you have problem with the equations when you're doing a regular derivative, if you found difficulty, maybe you can change to this implicit. You can add ln. Maybe you can square it. You can add many things in the equations. Okay. You can also do this for yeah, we can do it for let me see. So last time we have the ln x, right? Right. We can do it for the implicit differentiations. Uh, but let me start with the. Let me move here. Let me start with the x to the x. Okay. Start from this one first. So you can use this implicit differentiations. Okay. And adding the ln. You can try that by yourself. Okay, at least to solve the x with the power of x, I have two solutions. Okay? I have two solutions, and it's both correct. Okay. So first, let me just use the implicit way from previous page. Okay. So if I have y equal x to the x, okay, let me add the ln y, ln, okay, and it will be ln y is x ln x, okay. And let me derive this ddx. The left side become 1 over y and dy dx. Okay. The right side is having a product rule. It's fg. So f prime g, g prime f. Okay. So it will be 1 plus ln x, right? It's from the, so if fg, so f prime g plus g prime f, this should be ln x plus g prime is 1 over x and it's still x, so this will become 1. Okay, so 1 plus ln x. So dy dx in total is, let me bring y to the right side and change back to original equation, which is the x to the x, and then 1 plus ln x. Okay, that's the one way for this number. The other way, I can make this y x to the x, and I can rewrite this as, okay, I can rewrite with e. Okay, this is actually when we change to this Euler form, this e form like this. This is quite useful, especially when you are dealing with the with limit. Okay, if you're having any indeterminate forms in E, this is a good way to express the solutions. So when we are dealing with this, let me write this as, and we know the derivative of e to the x, right? So the first derivative is just e multiplied with the x ln x, which is 1 plus ln x, right? And this is the whole thing that is actually, we are going back to here, and this is just the x to the x, 1 plus ln x. Okay, same solution. Okay, same solution. Okay, so you can have any way you want. Okay, I think for most of the part for your practice, okay, I hope you get familiar to implicit differentiations because it has many uses. Okay? It has many uses for many equations that include y inside the equation. Okay? So implicit, I hope you understand the concept. Okay. Okay. So for the first one here, the ln x, like we already discussed the ln x last week, last Monday. So let me write this y is ln x, okay? And we can always do this, okay? Okay, it's correct? It's correct, right? I can do this. So I can write this as e to the y is x, right? Right? From here to here, is it correct? If I have y ln x, let me write in step by step, okay? And y is log e x, okay? So e to the y is x, okay? Good thinking, okay? But I always skip those parts and just add e, and it is always correct. Okay? And then let me implicitly differentiate this part. Okay? So dx. So this e to the y becomes still e to the y, but you need to multiply the inside functions is only y, and it's become dy over dx. And then it's equal 1. So dy dx is 1 over e to the y. And what is y? Y is ln x. And this is, okay? You can also prove the ln x with the implicit differentiation. And it is way faster than limit blah, 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 right? But still, definition by limit is the basic concept of derivative, okay? So if you see a limit fx plus h minus fx over h, that is really basic. Okay, that's really basic. So you can prove all the basic derivative with that. But later, if you need some encouragement in proving, you can always use the implicit differentiation as your tools. Okay? Okay, any question first? Any question first? Okay. Okay. So I hope you get the idea. Okay. Because in practice, it's actually really simple. It's actually really simple. Okay. So let's back to here. Maybe I will show you this one. So this part, okay, like square root of x plus square root of x plus square root of x, and it's plus as infinitely amount of x. Okay. So let's start. It's like playing a game. Okay. So let's just having y as our whole functions. Okay. Okay. Let's just let our y like that. Okay. Okay. Can I make this x? Okay. Because it's infinitely amount of x. Okay. So basically this part. So this part, the second part here. So plus, can I write y? I can write. Because as by definition, it's the same. It's going infinitely amount. Okay? And then let's square this. Okay. And it's become to y squared x plus y. Okay. And then what will happen? ddx here. So it will be 2y dy dx, and then 1 plus dy dx. Okay. That's grouped all together. So dy dx is 2y minus 1, okay, is equal 1. Okay? So my dy dx is 1 over 2y minus 1. And let's bring the real y into the equations. So y is 2. Get that? Okay. So from the equations that almost impossible to solve, like infinite amount of x inside that square root, okay? But with the implicit differentiations, with some tricks, okay? And then implicitly differentiate the equation, we can solve this actually. Okay. Okay. Other things that I want to make some points. If you have fx is cos x, okay, your first derivative is negative sine x, right? What will happen, okay, if you are asking the 27 derivative of fx? So meaning 27 derivative is the derivative, like it's the first derivative, second, 3, 4, until 27. What will happen? Okay. This is also a good way to observe any problem in calculus. So this is how you are using patterns, okay? How you are using patterns, okay? So what patterns mean, okay? So if you have fx is cos x, you have f prime, this is minus sine x, right? If you have the second derivative, okay, it will be negative cos x, right? What will happen the third one? It negative will be sine, right? And the fourth one, it will be cos x, right? So see here, okay? The first original equation is cos, okay? The fourth derivative is cosine, okay? So it's going back to our original equations. So 5, 6, 7, 8 is going through the same patterns. And the next, how many hundreds, thousands is going to have the same patterns, right? So if you are asking 27 derivative, we can see from here, every 4 times here is back to the original equation. So we need to find any multiplication near this 27 for 4 multiplications. So 4 multiplied by what? Nearest with the 27. So we need to find 27. We need to find 27. This is can become from 4 multiplied by 7 is 28, right? So when it is 28 of fx, okay, it will be the same original equation. So before 28 is 27. So 28 will be here, and 27 will be here. So 27 is sine x. So so this is so this is the original equations, and 27 become the less than 1 pattern from the 28. Okay, so whenever you find any, usually they will have trigonometric, because trigonometric, it will have a pattern, sine, cos, right? So whenever you have any equations related to trigonometric, and it's asking like how many patterns they have, even though maybe you will have, for example, okay, I can make the cos x is like squared like that. What will happen? You just need to add the multiplication of that function inside, right? So maybe here is becoming 2x, it's the x squared, and then maybe it's going x squared, and then 4, 8, etc. And you also can conclude that it will conclude 2 with some pattern here, right? Some number 2 with the power of n. You can also have patterns like that. Okay? And also you can have pattern in product rule, okay? But it's quite complicated, but it's still a pattern. Like for example, if you have x in the front, it will have like a product rule. but it will be a pattern also. As long as it is having a trigonometric and it is repeatable, and it will bring back the original one, you can use these observations. Okay, you can use these observations. You can find when the functions will be going back to its original equation. Okay, one way to solve calculus problems. Okay, I think we can go for some Lopital Rule, and then after Lopital Rule, maybe in the last 20 minutes, I will get into related rates. It's quite, it's simple, but how to understand the question is quite, it takes time. It takes time because it's actually like a story, and you need to relate the story with the rate of change. Okay? I will tell you later. Okay, let me move now for the Lopita Rule. So I will write the Lopita Rule in general. So Lopita Rule. So let me write this. I have f and g as my functions. It's differentiable and it's continuous. And then my fa, some constant a, okay, is 0. Also g of a also 0. And the second one, the f prime, g prime, they are continuous. And then the last case is when you are plugged in the a into the derivative, it's not equal 0. So you can write, in general, Lopital rule is when you have limit as x approaching a of function f over function g, this is actually, we can approach this in the first derivative of its function. So you need to derive the top one and the bottom one. I will visualize what's happened in Lopital. Okay, but before that, let me write some interesting proving. Okay, it's not really hard proving the Lopital rule, but I hope you get what the idea is. Okay, so if you have the limit of over g, okay, let's just think that when you plug in a, you know from our definitions, okay, fa and ga is 0. Okay, so I can add this fx and gx. Okay, I can add minus anything that I can do with FAGA, but let me minus this with FA and minus this with GA. But because FA and GA is 0, I can do that, right? Because it's 0, it's 0. It's still the same as f of x, okay? And then let me multiply this with the 1 over x minus a over 1 minus x minus over a, okay? So the top one will be okay. From the definition of limit, these two terms, this f and g minus something, x minus something number here, is the derivative, right? It's the derivative. So from here, actually, it's kind of, we can see that, oh, actually, it's the derivative itself, okay? So we can say that this is actually f prime a over g prime a, right? At least from here, we don't really need hard proving this L'Hopital, but we can see that, okay, this is our derivative, right? Okay. So let me use some another example, okay, to prove intuitively proving what is the Lopital rule. Okay. Am I too fast? Too fast? Too fast or no? No. Okay. And we still have like if it is confusing, if you're confused about something from the courses, and maybe you are nervous or shy to ask, maybe after the class you can ask me, okay? Or maybe next week also fine. Okay, let me write some functions. Okay, let me write these functions. And the question is limit as x approaching 1 of fx over gx. Okay. Both are when you plug in 1, when you use 1 in the either f or g, it will be 0, right? When you substitute x with 1, right? So we can use the Lopital rule. You can use Lopital rule and easily derive the f and g, right? But what I want to show you is what it really looks like, what is really Lopital rules in visuals. Okay. Let me draw here. Oh, it's not straight. It's curving. Okay. Okay, so let me write this. This should be plus 4, right? 4x minus x. Okay, so I should have 1, 2, 3, 4. This. And my maximum point, it should be at the here. Put this -1. Yeah, just make it until here. Yeah, more or less, the first function is the, let me write this is f of x. Or maybe I will, because I need this space here, let me write, yeah. And I will use the other color to describe the ln. Okay, maybe that is the ln. Maybe just gx. This is gx. This is fx. Okay. Now I have this graph, right? So if we observe the x equal 1 here, okay, both are at 0, right? At 0. Well, by the way, if you draw the graph, all the graphs like f over g in the some graphing website or any calculator graph, you will get the limit number actually. How much is the limit? Okay, but here if you draw one by one, you see that both of them are 0 here. Okay? Remember, limit concept is not always about the point at that x. Limit is about concept of getting near, getting close, close, close. Okay, so let's take our close range here. Okay, if you see, zoom this part. Okay, any curve you have in any functions, when you zoom in that curve, you will see like a straight line, right? It's like you are going in and see the gradient itself. At some point, it seems like the straight line. If you are taking straight line all the time, and it will be your gradient at that point. Okay. So for example, if in here I see here, if I'm zooming here, it's simply it's only straight here, right? And it's straight here. So let's take a close look for that gradient. Okay. So imagine that it's really, really close by the zero number. Okay? So I will write this as, let me use blue one, maybe here. Okay. So I have this triangle. So I have this triangle. Let's say, because this is the f, okay? Let's say this is the f, and this is dx. Okay? My gradient is df over dx for that one, for that part. Okay? And let's see the red color. Okay, let's see the red color. Maybe here. Okay, let's say this is the dg and this is the dx, also dx. Okay, so we have also dg over dx, and it will change as it's move on, right? So I can have my ratio for the gradient as ratio of the fx and gx. The ratio df over dx over dg over dx is always the same, the ratio. If you compare df, dx, dg, dx, it's always the same, okay, the ratio. So you can also think of that df over dx is the first derivative of f, right? d dx f, and this is d dx g. Okay. Intuitively, what we can do here is we can see that at this point here, as it's nearby this zero, you can observe that gradient, which is always, the ratio will be the same on every point, the ratio of df and dg. Okay? And that's why we can simply say that if you want to observe that point, which is zero, that is the same as its first derivative. Okay? By the way, the Lopital Rule, the inventor, he invented before derivative was invented. So it was not like this. It's not like the first derivative. He just said that, okay, in this closer by, you will have always, the ratio is always the same. Okay. And limit is also wasn't invented yet when Lopital Rule is invented. So yeah. And the Lopital Rule is not invented by Lopital, actually. Maybe I tell you before. So the Lopital is actually invented by Bernoulli, the physics Bernoulli in physics, the same guy. But he didn't have money to publish something. And then there's a guy who has money, which his name is Lopital. Okay, you work for me, I give you money, but let me my name be the inventor. And that's what is Lopital Rule. And that's true, by the way, that's the fact. So the guy who invented Lopital Rule is actually Johann Bernoulli. Yeah. Money is important. Yeah, poor Bernoulli. Okay. Let's check this one. Okay. This is also another proof. Okay. This one is sine. This one is sine pi x over x squared min 1. This graph. Okay. The question is when limit is x approaching 1. Okay. When you plug in to both of the sine or x squared, it becomes 0 over 0, right? But when you draw in the graphing calculator, you can get the real limit value here. When x is 1, it's going here, it's this p. It's around negative 1 point, maybe 6, yeah. around that point. So if we draw in separate graphs, okay, we can also solve the similar situations here. So when you are approaching the 1a there, okay, the red color is the x squared minus 1. Okay? So this is x squared minus 1. The green one is the sine pi x. So when you are approaching this one here, when you're approaching from here, here, it's actually going to 0, right? Each function. But when you combine, it's at B point. Where does B point comes from? It's come from this triangle. If you remember the triangle I drew before, the red color here, and the green one is having here. When you reach this, the ratio, the triangle above divided by, or this one divided by this one, the ratio will be this blue one. Okay, you can check if you have a good proportion, good scale. You can check with your ruler. It will be the same ratio. And remember, the gradient can be negative, can be positive, depends on how it looks like. Okay, this is positive, this is negative. Okay, and that's why you have negative, because it's having one is negative, one is positive, right? It's negative. Got it? Got it? Got the idea from graph? Okay. So actually, you can prove any Lopita rule from graph. Why is negative? Because one is negative, and you need to divide this one with the positive. So it's negative. That's why it's negative. Okay. Enlightenment? Clear? Okay. Okay. Another thing about Lopita rule. Okay. How to use Lopita rule. Okay? This is also important. How to use Lopita rule. Before I mentioned it's 0/0. Okay. So why is 0/0 situations? So let me explain to you about the indeterminate forms. Okay. So let me start with this number 1. Okay. So this form is called the indeterminate forms. So if you find this in your problems, questions, this is called indeterminate forms, which is we cannot yet determine. So it doesn't mean it doesn't exist. No, that's different. Okay, doesn't exist is not the same as indeterminate. Indeterminate means we cannot decide which form is this. We need to think more about this form. Okay, so if you find 0/0 or infinite over infinite, this number 1 case is able to be solved by Lopital Rule. Okay, so when you find like this limit, x approaching 0, x squared minus x, x cubed plus x, it's 0/0. You can always use the Lopital Rule. But Lopital Rule is not always the fastest way to solve. Sometimes it depends on the functions. Sometimes you just factorize and it will be faster. Sometimes. And maybe rationalize is also faster because the square root, if you derive, it will be like another square root. Maybe you have difficulty to calculate that one. Maybe just multiply by rationalizing with the square root, another square root. Maybe it's faster. Okay? It depends. Okay? So the first one is the original Lopital. Okay, let me say just this the basic Lopital. So whenever you find 0/0 or infinite over infinite, you can use Lopital. Why you can use infinite by Lopital? Because 1 over infinite is 0. So it will be the same case when you flip. Okay. Okay. Another one is this 0 infinite situations and infinite minus infinite situation. This is also called indeterminate forms. Okay. So when you find this, you cannot conclude what happened with this function. And also this functions, you cannot compute. Oh, infinite, oh, 0. No. Let me tell you about infinity. Okay. So infinity, okay. So infinity is abstract, not a number. When you write domain all real and you write in infinity, you need to write this with open bracket. Okay? do not make this close. Okay? Infinity is not a number. You cannot compute any infinity. Okay? It's an idea. It's abstract. It's huge amount, but you cannot. You don't know how much amount is it, right? So that's why we can also compute this negative infinity minus infinity. We cannot compute. Also, 0 multiplied by infinity. We cannot compute this. This is like which one is going first? Is it going 0 first or going infinity first? It's like a whole different subject, and compute as one, and we cannot decide which is it. Okay, but we can solve this too by Lopita Rule, but we need to rewrite the form. Okay, so the idea of Lopita Rule is always going back to the first case. Okay, so the second case is, for example, you have this x ln x. Okay? When you plug in 0, this 0, ln 0 is going infinity, right? Your ln graph is going infinity. So you don't know which one is going first. Is it going 0 first or going infinity? Okay. Then this one came up, so we don't know what is the answer. But we can write this as a fraction. We can write this in terms of ln x 1 over x, and it will be infinity over infinity. That's why we are able to compute this one with Lopital Rule. We need to change the form, and we can compute with Lopital Rule. It's doable in this way. Okay. Also, if you have, for example, this one, you have 1 over x minus 1 over sine x. You have 1 over 0, 1 over 0. It's infinity over minus infinity, right? It's also indeterminate form. What we do, we need to simplify this form. Okay. Conjugate this form into 1. And we have this form, and we can have 0 over 0. Okay? So the idea is all the indeterminate form, aside from the first case, okay, like this second case, bring back to number 1. Bring back to number 1, make it 0, 0, or make it infinite, infinite. Okay? This way, we can compute with L'Hopital Rule. And you can use L'Hopital Rule as many as you can, as long as it is still 0 over 0. So you can just L'Hopital Rule 1, L'Hopital Rule 2, 3, depends on the function. Okay? Depends on the function. And you can use as many times as you want. Okay? And the other case is 0 with the power of 0, 1 and infinity and 0. Okay? So 0, 0, it's indeterminate. Okay? If you have like 0.00001 and 0.0001, try to compute that one. It's messy. Okay? And we can conclude this is indeterminate. 1. Okay? Logically, if you think 1 multiplied by how many number is it? It's 1, right? But actually, because infinite, again, it's an abstract subject. It's an idea. We can compute this, what this really is. So this whole one with power of infinity is also indeterminate. Also, infinite with the 0 is also indeterminate. Okay? Maybe you are thinking, oh, with everything with 0 is 1. That's also wrong cases. So infinite, again, it's idea, it's abstract. You cannot compute this as a number. Okay? Then how to do? Like the x to the x before, it's 0, 0. Okay? So this is the form that I previously used. We can use this one. Okay? And we can make it like this one. And this one become the second case. And the second case, we can make this first case ln x over 1 over x, which is infinite over infinity. And we can compute this limit. Okay? And because this limit is only considered only this the power index of e, we can remove the limit only considering this whole ln x over 1 over x, because e is always e, right? Always a number. Okay? So we can use this and L'Hopital this one, and you get the value of your limit. Okay, that's all about L'Hopital Rule. So the idea is just rewrite all the forms that you think of, like indeterminate forms, change those forms into infinite over infinite or 0 over 0. And you can derive top and bottom. And you can derive as many as you want. As long as it is having 0, 0, you still can derive, as long as you want. Sometimes, sometimes one try and you get the answer. Sometimes twice, maybe sometimes third. Okay? Depends on the functions. Okay. I think we have only around 30 minutes. Maybe I will write the, before we go into related grades, maybe I'm just going to show you to example, one example for related grades. But before that, I forgot to mention the inverse, okay? The inverse. So let me go back to the inverse. This is your graph before. Let me go to the inverse, okay? It should be the inverse of trigonometric functions. Okay, so for example, sine what? Pi over 6 is half, right? Yeah, 1 over 2. Okay. If I write sine inverse of 1 over 2, it's pi over 6, right? Okay. Okay, so let's start with the, if I have tangent inverse x, okay? If this is my functions, can you find the first derivative of this inverse? Or have you learned before? No, right? Inverse for trigonometric? Haven't, right? So let me tell you some useful approach or observations so that you don't. There is a good way if you memorize the answer. The answer is the 1 plus x squared, but let's just remove this answer for first, okay? So the idea of the inverse, okay? If the inverse of the trigonometric is about the angle, okay? The angle theta or any pi over 2, pi over 3, okay? Let me write this whole tangent inverse, okay, as our just theta. Okay? Theta is any angle in those conditions, okay? Let me write this as theta. So I have tangent theta is x, right? By the inverse conditions, and I'm reverse the inverse and becoming tangent theta is x. Okay. Okay. My suggestions: draw the triangle. Okay. Write the theta here. So the tangent theta will be x. Okay. So it will be x and 1. Okay. Got it? Y over x, right? X over 1. And the hypotenuse, let's just compute the hypotenuse, 1 plus x squared. Okay? And because you already learned the implicit differentiation at the beginning of the classes, so let's just write, let me write here, the tangent theta is x. Okay? Let me differentiate all these equations. Okay? It's the same as when we derive and there is y, right? And now it's theta. Just change y to theta. Okay. So tangent theta, the first derivative of tangent is secant squared. Okay. So secant squared theta, and don't forget to write the implicit results. It's d theta dx. Okay. This is what we need to find. The first derivative of the function is d theta over dx. And it's equal 1, right? So d theta dx is 1 over secant squared theta, which is cos, right? This is equal cosine squared theta. Okay. Secant, cosecant. If you have cosecant, it's sine. Okay. If you have tangent and you have cotangent. Oh, by the way, do you know why the name is cosine? Why is the name is sine, cosine, tangent, cotangent? Tangent is because it's tangible. Okay. Cosine is because it's complementary of sine. Okay. In graph. And secant and cosecant is complementary each other. Okay. So from here, we know this is the cos theta. Okay. Back to the triangle. What is the cos theta here? It's 1 over the hypotenuse, right? And we square both become, and that's why the answer is 1 over 1 plus x squared. Okay. You can memorize this. It's good for you. It's not really that hard to memorize. But don't forget to going back in step in case you're forgetting. Because personally, honestly, I always forget, oh, which one is tangent. Is it 1 over 1 plus x squared or using the square root? I always forget. So I'm going back, always go to the triangle, define the theta, and derive by yourself. And you will always get this 1 over 1 plus x squared as the tangent inverse. So this is the d dx of tangent inverse x. You can always use this method to find, for example, finding the sine inverse x and then find the cos inverse x. But I will leave that to you, okay? Finding the sine inverse, cos inverse. And then from here, we can also combine with the other trigonometric as a composite functions. For example, you have cos, and then inside the cos is sine inverse. And it is possible to derive this also. Okay, this is basically the chain rule. So this cos, whole cos will be minus sine, and you need to multiply with the inside, derivative of the inside, and you need to multiply that, and you just multiply and combine together. This is also possible to check. Okay, but I will leave that to you and maybe your TA when they have the exercise. Okay. I will go to the related rates. Okay. Let me check my time is okay. I still have time. Okay, this is inverse of trigonometric. If we have time, maybe next week also I will review this in case you need a review. So here's the related rates. Okay. Okay, let me just give you the example, and then I will give you what you need to do in whole related rates problem. Okay. So for example, okay. So you have two events. Okay. The first one, the left one, and then the right one. Okay. Imagine if this is a wall. Okay. Any wall you can think of. Okay. This is a wall, and you have a ladder. Okay. Let's say just the ladder is 5. So it's easy to compute. The other one is 3, 4, 5. Okay. Just make it 5 meters, the ladder. Okay. And the ladder will be slipping down here. So it will be going down. Okay. So it will be going down. Okay. So ladder slip, and maybe you know the velocity from this direction. This velocity is maybe 1 meter per second. And you are asking how much the rate of change in the x direction. Uh, how are you going to solve this problem? Okay. So in any problems for related rates, okay, why it's called related rates? Because you want to relate one rate to another. Okay. So first, how to relate those two rates? You need to find the general equation in this problem or other problems. It can be about the area, how the area increasing. It can be about the movement, and there will be maybe like a triangle here, like something move, and then it's like a triangle. You can use Pythagorean theorem to make the relation between x, y. Okay. It can be volume. If like something getting bigger, you need to know the rate of change of that volume. It's also possible. So let's just write the Pythagorean theorem. So let's just write that just 5 squared. Okay, I have this these relations, and this is basically the positions itself, right? The length of the 3 meters, 4 meters, and 5 meters. It can be written as it is. Okay. So why I'm writing in x and y? Because later it will be changing in x and y, right? In the second case, the x and y is not 3 and 4. It's changing, right? So the whole equations I can write as x squared plus y squared is 5 squared. And then every time you are doing related rates, this is always the case. You need to just derive this with t. And because you know the implicit, so we can write all with the, so it's become 2x dx. Let me write it over t, and then plus 2y dy over dt is 0. And from here, we can get the idea for the 2x over dt. Let me write this as 2x is actually negative 2y dy dt. Okay. Do you know why this one positive, this one negative? Because when you see the ladder, when the x is getting larger, the y is getting smaller. So it has opposite signs. One is increasing, one is decreasing. When you relate to physics, velocity is factor, right? It depends on direction. If you make one direction positive, whenever direction from opposite came from opposite side, it will be negative. Okay? So in related rates, positive or negative, it depends on your view. As long as it is correct, whenever your conclusion are either positive or negative, as long as your view is correct and logic and makes sense, it's okay. So it can be like maybe the answer is negative 10 or 10. Both are correct. Both are correct. Okay? Both are correct. That's fine. So so let me write at x equal 3 and y equal 4. Okay. This means I'm using so dx over dt and dy over dt is my instantaneous, just write instant velocity. Okay. Remember, the instant velocity is velocity at exact point, okay, at exact time. So because our information we have is only 3 and 4 for this x and y, so we can just use this 3 and 4 and put back to equations. So 2, 3 dx dt, and then let me just 3 because it's canceling each other. So I will cancel this 2, and then negative 4, and dy dt, because it's getting smaller, let me make my dy dt negative, okay, because it's getting smaller. It's 4/3 meter per second. Okay. If you want to make the smaller is the positive one, that's okay. That's still fine. As long as it will be the other one will be negative. That's still fine. But it seems difficult to imagine how it's getting positive. But I think getting smaller is reducing. Okay, maybe we can take that as our negative one. That's also fine. But if you take just like, okay, just velocity, not really thinking about the smaller length, maybe just making it positive, that's also fine. And you will have the negative 4/3, which means this one is having great opposite sign from the y directions. Okay, because y direction is going smaller, the x direction going larger. Okay, you can take negative or positive. In later cases, also it's quite possible. Depends on the case. It depends on the case. As long as you are consistent with your signs, you always correct with the answer, the number. Okay. Okay, so mm, so the idea of the related rates, I will write some points for you. I think that just the summary. Okay. So first, find the relations, and then chain rule, and then differentiate. Yeah, just these three. So you will have like a story, and then the story in the story it will be involving the some rate of change in any possible way, movement, area getting bigger, smaller, and then connecting this relation with the chain rule. And all the chain rule will be about the ddt. Okay, we will always having dt, okay? dy dt, dx dt, maybe something dt dt, because its rate of change is related to time. Okay? Most of the cases, and then differentiate both sides, meaning just using the implicit and having something dt in your equations. And usually that dt, one of the dt is known and the other dt is unknown. Usually it's asking the unknown one, and then I'll find the unknown one. Yeah. But in the real problem in the textbook, it's quite complicated. Usually it's quite complicated. For example, I will show you just one example. Maybe we don't have time to finish it, or maybe the other one here. I have the answers actually. But let me just show you this one. Okay? So you have a circular plate. Okay, you put in oven. I don't know why the question just put in oven. I don't know why. But then from that oven, it's heated. Okay, like if you have like a coin, and the coin will be getting larger. Okay, so the radius increase. Okay, radius increase. And from this question, the radius increase. You have the rate 0.02 centimeter per minute. That's the increase of the radius. That's the rate of change. Okay, and then at what rate is the plates of the area increasing? So it's asking the rate of change of area. So before it's the radius. Now it's asking how about the area? Okay. Blah blah blah. When the radius is 60. So at 60, what is the instantaneous rate of change? Okay. So we can think of this as the coin. This is the radius. It's getting larger. You know the radius over dt, the rate of change is 0.02 from the questions. And you know that the area of the circle is just pi r squared. Just differentiate this area. Okay. Differentiate this area, become 2 pi r dr dt. Okay. And you know the r is from this at radius 60. The r dt is from 0.02. So you get the area over time, the rate of change area over time, and you will get exactly the number is 2.4 pi centimeters squared over minute. Okay. This is just a simple, the simple one. Okay, the simple one. Okay, I think in the textbook they will have a simple one and then the intermediate and difficult one. Usually, it takes like a paragraph. So, if I have this question in the exam, I will make sure you understand the questions. Okay, wait. Okay, I will make sure you understand the questions and make sure you understand how to deal with it. Okay. So I think the class is until here. Okay. If you have any questions,